Hello everyone, my name is Ivan Mlinaric. I'm a hand cache engineer. Um, I'll, I'm joined here with my colleague Brandon. He's gonna introduce himself.
Hi, I'm Brandon Bryant. I'm also an engineer at Handcash.
Yeah, so we came to some idea to make some educational videos from our team. Um, and first thing we're gonna present today is how to rather quickly and easily build a notary service. With the tools available on Bitcoin BSV, also utilizing Handcash Connect SDK. We're also gonna go a little bit through the theoretical part first, so we understand those concepts, um, and hopefully demonstrate how easy is to build like a working prototype of a very powerful feature. So we're gonna start with hashing, like cryptographic hashing. This is one pretty good resource on the internet in which we can look at. So Brandon, maybe, yeah, by the way, Brandon wasn't aware what we're gonna be going through. He's just gonna be here to, you know,
Ask
ask
questions.
questions, yeah, and hopefully challenge me enough so I present this in an understandable way. So yeah, maybe I ask you here a few questions. What is hashing basically in cryptography? I mean, we can read this, but what would you
Yeah,
say is important?
my understanding is a hash is a function that takes an input and then the output is always a specific amount of characters. And that output is deterministic based on the input that you always give it, but the output is generally always unique. Like there's small chances of collision, but um, whenever you put in an input, you get the exact same output, and it appears random.
Yeah, I think that's a good description. Well, collision, it's usually collision resistant. There's almost like zero chance there would be two different messages that produce the same digest. digest. Also important property is it's temper resistant, which means just a small change on the input would result in completely different result. Um, and as you said, the output can be of any size. Actually, input can be of any size, but the output will be always of the same size. And it's also quick to compute because that's kind of important, as we'll come to this a little bit later. So,
It's
yep,
it's impossible to go backwards. You can't be given an output and find the input.
exactly. That's a very important property. Um, so um, I built already a few pieces of code to demonstrate those functions. Um, um, so there's a I built this top file. I'm just gonna say a few words. It's very simple. It's async block, and we just proxy basically all the um, arguments that we will send through command line to a certain example. So we start with hashing. We just slice away first two or three parameters because they are useless, right? Like node, file name, and so on.
Right.
Um, so for example, if I look at hashing example, it needs a message and it will convert it to buffer and then it's gonna hash it. Um, Hash is a very simple function. We're using no dependency, just node. Yeah, by the way, we're doing this in JavaScript. The reason is pretty readable code for everyone, but it's probably not the best one, the best language for these kind of things. Uh, but for demonstration, I think it's great. So we're doing hashing here, and that's it. And we display it to the console. So if I try an example. It would go something like node. The file is here. And now we're going to say hashing as which example. And we're going to try to hash something like today is a nice day. Okay. Oops. Oh yeah, I think those letters are not supposed to be in the front. They were here since before. Yeah, okay, so that's the hash. So if we just change one letter, result is completely different, right? So that's fairly simple. I don't think we have to say much more about it. But the upgrade of this is maybe hashing files, right? So instead of a message, we can do a file. This is an even shorter example. We would take a file name, convert it to buffer, readable buffer, and then hash it through the same function that we saw before. So this time, instead of hashing, we will say hashing file, and we need some file name. So for example, I know there's a readme there. It's also. So maybe now if I go into this readme and change a character, I'll put another G here. Again, a very different result. Now, what's also maybe interesting here is I'm gonna hash a bigger file. For example, I prepared one that has like 40 megabytes. It's some haste game. So also 40 megabytes was very quickly computed, right? Okay, so I guess that's enough about hashing, and we can move to the next topic, which is called mining, proof of work. So what would you say about mining in this context of notary service?
So the miners are keeping track of this public ledger, because if you want to have a notary service without any third party, you need to have it on a public ledger. Like, it can't be private. So proof of work mining is a way of updating a public ledger in a way that it makes it really expensive for like a malicious actor to cheat.
Yeah. Also, there is a good article, maybe we're gonna put this in description, about how Bitcoin mining works more in details. But in reality, we don't need to know that. The most important things that I think in this context are mining is also hashing. It's brute force hashing, where we want to put as many different inputs inside, so we get a solution that fits certain formula, right? Like, and this is always controlled by how many leading zeros that hash needs to have to be like a good solution for mining, right? And the important piece beside storing data on blockchain is security is economic property. You need electricity, you need investments, you need energy to compute those solutions. And right now we have a very large collective investment which is continuously producing and trying to find those solutions. And if one individual would want to do this, it couldn't, basically, because it doesn't have resources. Like, economically it's impossible to do it. And what is also really interesting is very simple to check that this solution exists somewhere in the world. Like, we have a hash and another hash and another hash, and everybody can check that, right? It's not expensive. So I also prepared a little example for mining, just to see how it works. Now, when we look in Bitcoin, there's a few extra details. This is very basically stupid, but I think it demonstrates the thing okay. So yeah, you want to say something?
Maybe talk through what you're doing. So what is this previous solution that you're giving it?
Just a second, let me make this bigger. So you're talking about previous solution, yeah. So first, let me just go quickly through the algo. We're gonna send some Genesis message inside. So with just some message that we wanna hash for start, and then we are building a chain of those solutions, right? So first we need to find first solution, and based on that solution we can find next, right? Because we're hashing previous solution to get the new one, right? So, and the one thing that we can set here is difficulty. How many leading zeros we want to find for each block, right? Obviously in Bitcoin this is dynamic, it adapts every 2000 something blocks. Here we're gonna just make it very simple. So we want to find 5 solutions in a row. So once we find a solution, it travels back to find another solution, right? It just
so
goes.
You're creating a chain.
Exactly. I'm building a chain of 5 solutions with 5 leading zeros, and this is also like a trying mechanism, and I use the nonce, like I'm just increasing one number and appending it to previous solution, so it's changing until I have a solution that works. Like it's very dumb, but I can demonstrate with this few lines of code how it was supposed to work, right? So this time we're doing mining. Maybe I'm gonna use that first one. And maybe for start I'm gonna put a low difficulty. Oops.
So the difficulty is the number of zeros you want to find at the front of the hash.
Exactly.
So right, so you're using hexadecimal, so it would be 16 to the third power.
Yes.
How many tries do you think?
Yes. That's yeah. So that was pretty quickly. I found 5 solutions. First one was found after 5,655 tries. Second after 210. Blah blah blah. So now, as the moment I start increasing difficulty, maybe I start by one more. Okay, it already took a little longer. And this is basically with exponential with each zero here. So as we can see now, it's going way slower. It needs to try many more times to find a hash with 5 leading zeros. Right, so that algorithm is pretty bad. It's using just one thread, it's using CPU. But right now in the world, there are specific machines that are super optimized for mining, and they are trying trillions, or I don't know exact number of
Right. That's all they do. They're just like circuits that crash.
Exactly. And like I said, this is economic property. Like there's a lot of energy being burned, so we find those zeros. Now the next thing that we're gonna look into are Merkle trees, which is a nice concept integrated into the Bitcoin. And maybe let's check a little through the theory first. So yeah, so here is the standard, which is currently in being approved, defined. But Merkle tree, maybe there's some picture here. Not really. Yeah, let me see if I have some nicer. thought I had a good resource, but it didn't have a picture. Well, because it's really nice to see this through the picture. Yeah, okay. So, yeah, what do you know about Merkle 3 for start, since while I'm looking to find a good picture?
I actually don't know much about how they work.
Okay.
I would say I would just say so. There's one like top hash as you see, and through some magic or cryptography, you can verify the leaves of the tree.
Yes, true. So Merkle trees are binary trees, and they are trees of hashes, right? Binary trees means they always have two leaves. Well, it could be one, but no more than two. And you calculate the next hash by taking, you have to start, I think, wait, in the bottom, you put together, for example, here L1, L2, hash those two values together, and you get higher on the tree for the next node until you get all the way to the top. So for example, 0 and 1 together will construct the top hash here, and 0 through 0 and 0 through 1 will construct 0, and so on, right? But you start by putting all the, in this case, transaction IDs in Bitcoin in a queue, and then by pairing them together, you can calculate all the way to the top. Now, one thing to say is this structure scales really well because it goes exponentially. Every level deeper you go, you double the capacity of how many transactions you can put in this structure, right? So 2 for, the formula of putting a rice on the chessboard. By the level 30, the number is already huge, and by 64, it's out of the universe, right? So, and the second thing here is that you need all the transactions if you want to build the whole structure. So this is not very simple to do if the blocks are huge. Imagine there's terabytes or even bigger blocks. You would need the whole block just to generate one proof for one transaction that you need. So generating those proofs, as I'll show later how they look like, is generally more expensive operation. Not very expensive. Small blocks, it's very easy. But
Does
yeah.
does the order matter?
Sorry, I didn't understand.
Does the order matter? So you're given a block, so each transaction, is there a first transaction and a last transaction?
Exactly. The ordering is very important. If you miss just one, if you mess up the ordering, the solution will be completely different, right? Just one element if it changes. So the order of those is also very important. But, so for that reason, I chose a service that is doing this. And you only need this once. So if you're building a notary service on Bitcoin, at the time you want to timestamp something, you do this once and then you save the proof. And once you have the proof, you don't need the service anymore, right? So, because that's also important in the end of the day here, as we will see. So if I move towards the Merkle tree, I've built a little example which wants transaction ID. That's Bitcoin transaction ID. It will ask this what's on chain service to get this proof. I will also show the API. It's fairly simple. So, for example, this is how it would look. You send certain transaction ID. This was a small block because it only had two branches, and it would tell you each depth and if you have to put it on the left or the right in the tree, right? It can be either, depends on the position.
Is this a path? I'm a little confused on what the branches are.
Yes, that's path exactly. So for example, here it's saying, okay, your pair is this hash, and you are going to the left, or actually the pair is on the left. I'm not sure, and then you, for example, you are L1 as a transaction, but you need also L2. So the L2 would probably be here, that value here. And he's telling me, okay, that value is on the right. I'm not sure here. Maybe he's telling me I will check later in the algo, but you get the point, right? So as we further travel up, okay, now I hash those two together. I get a new solution. Now I have 0, but now I need 1, right? That 1 which is missing. So that would be then this one, and is also telling me on which side I have to put it. And then you hash it until you get to the top.
So a Merkle proof for a transaction in a really large block will have more branches.
Yes, the more transactions are in the block, the more branches there will be.
Okay.
But as I said before, it scales good because each branch is doubling capacity, right?
Right. So this example you did, this would probably be from a really small block, right? There's only 2 branches, so
yeah, I would say there couldn't be more than 4 transactions here, or even less. Yeah, I would say no more than 4. Yeah. Okay. Yeah, and one more thing, while it's a little harder to calculate the proof, it's very cheap and easy to validate it, right? It's just as I'll demonstrate now, fairly simple algorithm. As I said, I fetch this for one transaction, I get the proof. Then we send through that proof, there's a target hash. Target hash is in this case basically transaction ID. This is where we start with, and there's a root to that solution, right? We have leaf, root, and the proof in between. Those are 3 pieces which we need. And we just iterate through each branch, and based on if it's left, we put it, for example, if position is left, then target hash is on the right, and that pair hash is on the left. Otherwise, the other way around, right? And a Merkle tree parent we calculate by concatenating both values together. There's a little bit Bitcoin specific here. The values had to be reversed before concatenated. And once we have a hash, we have to reverse it again. That's like a little bit extra complexity, but we're just putting values together, hash them, and we have a new basically node, right? So that's it. It's very simple. So if I have some transaction, maybe I can find one on what's on chain for already. There's also important piece. Block already needs to exist. So unmined transactions do not have proof yet because there's no block to which they are assigned. So maybe I'm gonna take this transaction ID. It's probably a very stupid example. I'm gonna say Merkle tree and this transaction ID. So we got this this proof. As you already predicted, this block was bigger, so there's many more branches here, right? But still not that many. So that's hash, and that's Merkle root. One piece that I would say here is Merkle root is part of the block header, which we're gonna come to it a little bit later. And that algorithm immediately locally calculated this proof is valid for this hash and this root, right?
So if you ideally you wouldn't be getting the Merkle root from this service because it's like you're kind of like you're trusting the service to give you the inputs and the final result.
Yes, that's a very good comment, and I'm glad you mentioned it. Later, as we're building the notary service, we will want to get that root from somewhere else, right?
Right.
So the next thing after the Merkle trees are Upreturn. Now that's a very simple thing, and most people are aware that you can attach certain data, like here, for example, into Bitcoin transaction, right? So you can basically write whatever you want, some extra text, some other hashes maybe, and just include them in the transaction.
The script, so you can actually see the Upreturn you're talking about.
Yeah, so here's the Upreturn, and one piece that I would mention here: each transaction is constructed from inputs and outputs plus some extra data, and each output has its chunks, like this zero, Upreturn, this, and those are different chunks to each output, like different comments, basically scripts. So what I've done here is I've built a very simple parsing tool. Let me make this bigger again, which you send inside transaction ID and some value, and then we will fetch that transaction again. We add this wedge on chain service, and then we will check if this value is somewhere in the transaction, and that's very dumb. We just iterate through every output, through every chunk, and if that chunk is basically has a buffer, is not just a comment, and if that value is inside, we say, okay, this transaction has this value stored. It's like a proof. So we can immediately just use this case here. For example, the transaction ID is this one. Maybe some value that I can find inside, like maybe this one, because it's quite large, so it's more interesting. So so this one is called TX parsing, and we're gonna say this transaction ID, and let's check for this value inside, which also seems some sort of a hash. And we got a answer. It's a little bit large, but it's saying in this transaction ID for this content, it was found in this output, which seems like pretty large. It has a lot of other things inside. Maybe this word is a little bit.
So we're looking at a transaction that has this. In this case, it's an NFT in the Upreturn for a game called Cryptographic, which is a video game that uses the blockchain.
Yes, exactly. We can check, for example, if there was something written in certain transaction, exact value. For example, this was also found, but now if I put some characters, it will say not found, right? This armor color identifier FDD is not inside, right? So that's another piece. It's like I said, it's very simple. It's nothing. The most complicated piece so far was basically Merkle tree, and even this is pretty simple if you look at it, right? It's like 12 lines of code. So there's then another thing which we're just gonna mention briefly. Well, maybe not briefly, because I think it's important, but so we have a block header client. What do you know about this thing?
The point of this is so that someone doesn't need to run a full BSV node, because running a full node requires a lot of resources. So we just want block header is the root of the Merkle tree. We don't want to listen to every single transaction because that's really expensive.
Yes. So uh, the one thing that actually here I think is mentioned is this. This is actually I think taken from Satoshi's quote for many years ago, um, and it says like this: 80 bytes per block is basically a header. And this grows linearly. So for all the headers so far in 12 years, we are somewhere at below 100 megabytes. And in 5 years, it will grow maybe for 50 megabytes more, right? It's this can run basically on any device today, like a phone, very easy, can run something like this. You don't need expensive equipment. Um, it would be also maybe interesting to just quickly check what is in the header. Block header Bitcoin.
I think the other interesting thing is this block header light client listens to the peer-to-peer network directly. So it's not like you're trusting some what's on chain service. You're actually listening to the BSV network.
Yeah. So what you're saying is um, you don't need the service. There could be, and there is already a few tens, hundreds, maybe thousands of those clients, and they exchange this information. And the only validation is proof of work, which we explained before. So as long as some miner has found a solution and signaled to us, look, I found the next block. Apparently, a lot of work was put into it, and I can verify very easily that the block is valid, or the solution is actually valuable. I can accept that chain as the longest chain, and that header, as I mentioned before, is 80 bytes long, and it includes previous block, so it's a chain, and that Merkle root that we talked about, right? This is block has its own ID, but it has a Merkle root as a content of in the header, right? And plus a few other pieces which we're not gonna bother with now. So so yeah, everybody can spin this header client. It's very lightweight, and you don't need to trust nobody. It's like it will come to consensus based on basically math.
Mm-hmm.
Okay, so those are actually all the pieces that we're gonna use. One detail, this block header client we already use in the company, so I'm just gonna use it, but it's very easy to deploy and install locally if someone would want to. I mean, whenever someone would need to. Okay, I think I actually created a small example. It's made as a service which we can use, and we can give the block ID, and we will get that header info. Just a second.
What is the block ID? Is that the number?
Yeah, block IDs. If we look again into the Explorer, how exactly it's calculated, I don't care at this point. But each block has an looks like the block itself is the solution, right, that we talk about. So that
Right.
ID is actually so whenever we see a block ID, it has zeros in front, right? Actually, I didn't know that. I look at the many IDs, but I I just didn't I wasn't paying attention. So let me just check if there's something more. Oh yeah, we have an example of block header. We have to give in block ID, and we're gonna get some information out. As you can see, it's again basically that service that I showed. One more thing. We're basically just using 3 libraries: Handcache Connect, BSV library, and GOT, so I can access REST API. I mean, I can use REST API to access that what's on chain service. That's all we have. So let me test some block header. I would need, for example, this is a good. Let's try this. So it's dump. I don't know why I'm lazy to write a few words. I prefer to delete 10 times more. Block. Do you hear some background noises?
A little bit. I think
Yeah,
your
a
kid.
bunch of kids came home. It's a mess. Okay, so what does it say? Yeah, it's part of the longest chain. I think that's important. We can see the height. It's already confirmed 5 blocks deep.
Yeah, show
We can see
more.
Yeah, sorry.
Never mind.
And there's also timestamp, which later we will use. So that block was at this time mined, more or less. There's always a little bit of a window around, but
is that timestamp in the hash? Is that timestamp included?
I think it is. Yeah, here it is.
Okay.
So it's part base. It's actually mined, so you can't temper even the time. It's part of the proof of work. So those are all the examples that I wanted to show, and all the pieces that we will need. Beside also a hand cache service, which is I just built a small wrapper around the SDK just for convenience, but we'll get to it to this a little bit later.
To enable these later.
Yeah. So so the problem, I want to explain it here. We want to generate a proof that certain set of data or information existed in a certain point of time, and we don't want to trust the third-party notary service, and we want to be fully sure it wasn't tampered, right? So certain data existed at that time, and it was ever tampered, and we don't want to trust somebody else to be in between to say, yeah, you just trust me, that happened, right? We want a proof. So the solution that we came up with is timestamp content, hash it first, then store it inside the Upreturn of Bitcoin transaction. There are other ways to do this, but this one is the simplest, and I don't want to overcomplicate. Then we obtain the proof. The proof is, as we shown, Merkle proof. We will also store raw transaction and that block ID. And we're just gonna store that next to the content, like a metadata or additional file. And then we're also gonna have a validate function, which will read that proof, validate block information against the header, basically block header client to get the timestamp, validate the proof, and also check that hash. But will be more clear once we do that, right? So those are 3 things. The first thing that we want to, please say.
Let me comment. The thing that stands out to me is in the first step that you're hashing the content itself that you're going to put into the Upreturn.
Yeah.
So I guess that's going to make timestamping anything a lot cheaper, because you don't need to store all the data inside a Bitcoin transaction. You just need to hash it.
Yeah, this is actually, I even wrote this here. What are that's a very interesting conversation. Like, what are advantages if you're just storing hash or the whole content, right? That's a very good point. Obviously, it's very cheaper, right? I mean, no matter the size of the file, the price, I mean, the size will be always the same.
Mm-hmm.
You don't need cryptography if you want this to be private. Like, you don't need to like publicly share content. It can be completely private. Nobody knows
Right.
what is behind.
So
And there's, yep,
you you still need to keep the data around. It's not like your personal database.
exactly. Just that if you wrote something on blockchain, doesn't mean somebody's gonna store it for you for free. And even if so, will you be able to find it? Imagine there's terabytes every second coming out. If you lose the pointer to it, it's almost like lost at that point. So you still have to store something, like at least block ID, transaction ID, where it's being saved. So it's not like you
Right.
don't need to save anything, store anything. So the problem can become almost the same as saving that file somewhere securely. Plus, um, you can back up. The problem of backing up file is not a hard problem. This is a problem that's been solved many times. You can save in a million different ways. I mean, thousands of different ways and places a file or whatever you need, right? So that's I think pretty interesting to think about. Um, so we need three pieces, as I said, and we're gonna start with timestamping, and this is something we're gonna code. So I'm gonna add a new file. I'm gonna call it timestamp file. I usually follow the same structure, so maybe some simple. I'm gonna just copy it and rename it. This one is now timestamp file. So what would be an input to that to that file name? I think, right?
Or path.
Yeah, I'm gonna make it simple. I'm just gonna work in the current folder, so I'm not. So I'm making it simpler. So
Mm-hmm.
I'm just gonna make file name, and for some reason that doesn't work. Oh, because I already renamed it. So it's gonna be file name. Don't do that, kids. Do it from scratch. um, so yeah, I usually follow this pattern in all the examples just for so they look familiar to me and they're always the same. But anything would do. So let's start here. I'm also gonna delete those two functions because I don't need them. Yeah, I should have started from scratch, would be less work. So first thing, we want to hash the file, right? So I already did that. So hashing file, and there's a function that is called hash file. So let's look at it. It wants a file name. Okay, that's very simple. I'm just gonna give it to the function, and the result is a hash, right? So the second thing that we want to do right now is store this on blockchain. Now, it's probably not an easier library that you can use to do that, very simpler than with handcache. So I wanted to show the process of how you can. It's a little bit of a hack at this point, but we are in process to make this much better and much more obvious. So what we need to do is we go to the handcache doc. I don't know exactly the URL, but it's here under developers and documentation. Okay. So here is all the API, okay, and we will need to create something through the dashboard. For some reason didn't open on the first click. I already created one app here, so I'm gonna create a new one. And I'm gonna call this application something very random, because I'm just gonna use this for this example right now. Do you have some suggestions?
Notary service.
Okay. Notary service. I'm gonna put my... Please don't spam me. I'm gonna leave all this empty. I don't think I need anything of this. HTTPS. Why I'm doing this, I'm gonna explain once we use this actually. But I think everything else I can leave empty, except I wanna click here pay. I need the ability to pay. So let me submit that app. Okay, successfully submitted. Now if I go here, the two things that I need is app ID and that secret. As I mentioned before, I have already come up with a little bit of service, but it's copied from documentation. If we look at here, what you need is basically this block, and that's it. So you can connect that application that we just created, and then we're gonna use redirection URL and get account from the token. That's all we're gonna use to set up the infrastructure. So right now, app ID is this one, and the secret is this one. It's not that. I'm gonna revoke that later because we're gonna obviously show this to the public. So I need a URL that I will call, from which I will extract the token. This is a little bit complicated, and as I was working this, I realized, I mean, we already knew this, but this should be much simpler. So, but let's do it now. So, what I'm gonna do right now here is I'm gonna say and cache service and get URL. I need a URL for start, and I'm gonna just and I need to set this as a new task here. So we're gonna say timestamp file, timestamp file, and that's it. Okay, so let's get that token first. So no. File. No, I'll work with this Druid. Okay, so I get this URL, which I'm gonna call. And now I will authorize my wallet to this app that I just created, right? So I will be able to access my wallet and do payments programmatically, right? That's what we're doing right now. And once that is done, there was this, as you can see, local host, and I got this token here. That token is the access to all the magic that I will need, right? So once I have this token, I'm going back to that service, and I'm just gonna store it here.
Why are you using the pay permission if you're trying to timestamp a file?
Yeah, we'll get to that. So we're gonna basically be paying a little bit of money, um, and we're gonna attach that data on that transaction. Like technically, there's an edge case where we don't need to pay nothing, and we would just save data on chain. So there would be no output with value. Um, but I want to make this example a little more interesting. So for each time we do a notary service, we want to pay commissions to somebody. So we're going to come up with some formula, like maybe I will take a cut. Maybe we're going to pay Satoshi a 10 sats for his great work, something like that. We come up with some formula. Now that I have this, I think we can go back to this. So that was just temporarily. I put this here so I could set up the service and I can start paying. So now instead of so now we need to find payments here or attach data even. Maybe I'm just gonna copy the whole example here, like this. So I just made a convenience method, but all this code that is in this service could be in that class. I just like it to abstract it, so it's less code. Okay, if I just copied that example, Lara, I'm busy. Can you come a little later? Okay, okay. Ciao. Sorry about that. So yeah, so what we're gonna do? We wanna have an attachment. Attachment is a data that we're gonna put next to. I mean, we're gonna put in the Upreturn, right? So I was thinking something like that. Let's put something like maybe file name. And the second parameter, maybe we wanna put a hash, right? So we're gonna call this something like sat256 hash, and the hash we also have already up. So we're gonna store in the Upreturn the name, the file name, and its hash. And as I said, let's make this a little more interesting, and let's put maybe, what's your account?
Brandon Bryant.
Brandon, like this?
Yep.
Brandon Bryant, we're gonna send you some sets for, let's say, 100 sets for each. I don't know what's the verb for notary something. And
Notary.
And let me find Satoshi's address. Okay, let's find a block with number. I know that block number 1 is unspendable, so I'm gonna go with block number 2, and that address should be Satoshi's, right? It's high probability it's his. So let's give him a little bit of money for providing as a service. Okay, we could add obviously way more participants here, but just to show the example. So now let's do this. Let's timestamp file for real. And let's just one more thing. You can see this is obsolete here. Yeah. Okay, that was pretty quick. So this is the transaction that was created, and it has its ID here. So I guess best we just go to the block explorer and immediately. So it's here, and this is the Upreturn, and those are the numbers that went around. So we stored Druid latest DMG with this hash. Okay, so I think we successfully timestamped that file. So if someday in the future we will want to make a proof, it's stored on the blockchain. But now we need to find a simple way to create a proof, right? So the next step that we want to do is create proof, right?
Right.
Create proof.
And we're hoping that the transaction gets mined into a block.
Yes, so that's a good point. I think while I'm writing the solution, hopefully the block will be fine. Otherwise, we're gonna pause a little the video. Hopefully, we're gonna be lucky. So it's not like 1 hour till next block. Sometimes happen. So we're gonna call this create proof. It's gonna have a constructor. So what would be good input? I would say transaction ID.
Right.
So let's make that as a parameter. Let's make it private. Put some spaces. Execute. I guess we can make this to arrow function. Okay, so we already said we have a what's on chain service, which we can fetch the proof for this transaction. Now, the problem, as you just said, is there is no proof yet. We need to wait for one block. I guess I have nothing better to do until I have proof and I see it. But maybe I can just speculate what will I do after I have a proof. So if I have a proof, this needs to be a sync, by the way.
Do we want to verify a message in this?
Yeah, it would be an option that we be sure that we actually, how would I say, that we actually didn't make a mistake and given the wrong transaction ID. But I would rather focus on happy flow completely, right? Let's not think too much about the other flows.
So we need the Merkle root from our block header client.
Yes, let's do that. So is there header client, we call it header client service.
So we almost need to know the
block
height or I'm not sure. We need to know the Merkle root. So I guess we could grab that from the proof.
Yeah, that's why I actually wanted to see what exactly comes with this proof. Is there more? But we need block ID here.
Mm-hmm.
So once we have that, okay, we can import fs. We're gonna write into the file.
We just had a block 2 minutes ago,
okay,
so maybe.
we're lucky. say yes. Okay, we're also gonna use that. Okay, let's then just run this, and I'm gonna log it. And we're gonna come eventually to the solution. So what do we have in this proof? Transaction ID is here. Oh, I also have to do something else. This. Okay. Okay, it doesn't like something. Maybe it's not the proof there yet. Let's check. Maybe it wasn't mine, but it wasn't included. No, it's still unconfirmed. Yeah, we're gonna have to wait a little more. I'm gonna put to pause this recording until we get the block. The still no block finds, but we're kind of bored, so we're just gonna continue doing this a little bit blindly. So the other thing that we will store in that proof is actually a raw transaction, and later I'm gonna explain why. Now we could store just the transaction ID, but I think it's better to store the whole raw transaction, and there's two reasons. Once we're gonna be checking the content for the Upreturn value, plus we can always calculate transaction ID out of it, right? So then we're 100% sure. It's much better proof than, and there's no redundancy here, right? I feel it's better like that. So what I'm gonna do here is I'm gonna store this in a file that's gonna be have the same name, but will have a different extension. So first we're gonna define how this proof gonna look. Maybe this one will be called Merkle proof. Merkle proof. This one's gonna be called proof. So we're gonna store it inside raw transaction, as I just mentioned, and we're gonna store inside Merkle proof. I think it's called branches, and those gonna be branches. And there's also block ID inside. Now we need to save this into the file, so we're gonna say f sync, and this file is gonna be called same as this one. So we're gonna say oh, we would need file name too, right, to add here. So let's do that. File name, and it's gonna be called proof, and it's gonna be JSON. And we're gonna put in JSON stringify that proof. I usually like to do this so it's more readable. And I think that's basically it. Let's let's check. Did we get some luck here?
Well,
Scheiß. Huh?
are we going to do any validation before we save it?
What would be the validation? We have to build validation first, right? We can then, once we have that algo done, we can also use it here. So we can immediately test it upon generating it. But we haven't actually built that piece yet. Because validation is two pieces. One, we need to check that hash is in the upreturn that we're looking for. And we need to check that transaction existed in some point in time. But when you're talking about validation, what do you mean? Which of those two pieces?
I guess both.
I guess both.
Yeah, I think I see what you're doing. You're just storing all the information needed to prove what you're trying to prove. You're not
Yeah.
actually doing. Okay.
And on top of it, that proof has to be with as little dependencies as possible to anything, right? That's kind of the idea. That's why I also actually didn't store Merkle root. I prefer to have block ID, and I will ask block header client what's the Merkle root for that block, right?
Right.
Yeah. I don't think we I want to proceed to the next step unless I'm sure this is actually yes, it's confirmed. So let's just test it out. So I also need to give file name here. Now, obviously there would need to be more checks, more validations, but like I said, we're focusing on happy flow. We want to make it work because that's enough for explaining the concept and showing how to be done. So I think that should be it. Okay, this is probably it. Was it? Yeah, that was on. Oh yeah, look what happened. So this was the proof. We got a block hash out of it. Okay, so we actually don't have block ID, we have block hash. Block hash. Block hash. So I'm gonna run it again. And there should be some file here now. Oh, that's wrong. I think I made a mistake. I think this one has to be turned around. Let's try again. Okay, that's better, right? So I've stored raw transaction, branches, and block hash. I believe that's all we need. So we have zero dependencies to prove something existed right now. And every time in the future somebody will ask me if that file existed, I'll have proof, which is very strong. Probably.
Right.
So what we need right now is to create the third piece, and that's validate proof. Validate proof. By the way, I already built this. It's here. I just have it in case I'll need to cheat. Someone asked why is here a solution. So let's build another class. Export default class validate proof. Tuck constructor. I think just file name should be here enough.
Is this the file name of the proof?
Actually, I think I want to just use the file, and I will assume the proof is next to it. So I'm not We'll simplify this. Execute. It's probably gonna be async. So, okay, let's just for start. No, I need to import an FS first. Import. This one is the right one. So first I just want to read that file, so I have it here. Const proof is fs read file async. So I'm just gonna steal that from here. Shit. Oops. And something else needed here? I guess not. And to my understanding, I don't know exactly, is it a buffer or string at this point? I rarely actually read files, we'll see. I think it's buffer. Maybe I can immediately convert to string. Anyway, I'll see. Console log proof. So I just can test this for so far. So index, we need a new task. It's gonna be called validate. What? It's here. So now I just need a file name, so I can remove that transaction ID. Okay, apparently I read the file successfully. So okay, now we have those pieces. So first step, as I mentioned before, would be good to check if that raw transaction that is there actually has that content of the hash. So first let's hash again that file, right? So we're gonna say hashing file. We're gonna hash it. Again, we don't want to trust nobody. We need to hash it again to be sure, right? So okay, we have hash. Now we have this other tx parsing and find Upreturn with value of that hash, right? And we need a raw text transaction that is stored in the proof. Proof raw text. I'm gonna call it chunk, and I'm gonna say if no chunk, it wasn't found, then I guess I can like throw error and say that file not hashed, not timestamped in this, file hash of this file hash
not transaction.
Not present in given transaction, something like that. I guess we can test this already. So if we put start validating, okay, it didn't work. So why is that? Let me think.
Are you passing?
Sorry?
Never mind. Never mind.
Did the file, did the change something? I made a mistake. Let me think about it. So, was the right transaction ID given? Yeah, this is just about the happy flow. Let me, okay, I'm gonna do something. Maybe is it the right transaction ID that I use the proof for? It's this one, right? 434. And well, I can check in the history. Yeah, it's this one. There must be something. Oh, maybe it's an async function or something like that. No, it's not. Is oh no. Oh, this is. No, I'm actually not sure.
Well, proof is a string, and you're never parsing string.
You're absolutely right. Thanks for this hint. Maybe it's gonna save me. I think it did. Yes, thanks. That toString was completely unneeded. I don't know why I added there. Thanks. So so far so good. Right now we can say just for fun, console log. We're gonna negate this one. We're gonna say. But we can actually make it nicer, like the same as there was in this example. Something like this, right? Except we don't know the transaction ID, but I can calculate it because that's also that we're gonna need right now. Transaction ID is actually also pretty simple, but again, some Bitcoin specific. You need to do a double hash and then reverse it of that raw text, and then you will get the ID. So I'm just gonna do that. I need to send in this. Oh, this is just normal chunk. For content, in this case, it's hash. Well, that's a pretty stupid string. Contains a hash. Contains a hash of a given file, something like that. Don't want it to complicate too much. Whoops. I was creating proof instead of validating it. Actually, that toString was probably needed. Oh, I think I know what's going on. I think this needs to be something like buffer, and then from actually to string. Forgot.
String and then JSON.parse.
Sorry, what?
So toString at the end,
Mm-hmm.
and then you have to parse that JSON. So in the front, JSON.parse that whole thing, the whole
Oh,
string.
let's try that. Thank you. That saved the day. I so rarely work reading files that I'm completely lost usually here. So right now we have confirmed then that that raw transaction contains that hash and Upreturn that we also calculated, but that means nothing, right? Anybody can put some raw transaction and fake it in that proof, and so what we need to do on top of it is that this is actual transaction that was confirmed in the network. So maybe if that was as a first step, I can put it in some sort of, well, I'll do that later. For now, let's just continue. I'm gonna put a few spaces. Right now, we're gonna use block header client service. It's called header client service, and we want to get block header info. For that proof, I think would be better if I call this block hash instead of block ID. I'll see how this goes. Const header info, and let's just print that for now. Oh, it's a promise. Okay, so one thing that I would actually check if that block is part of the longest chain, right? If it was orphaned, it's probably not very interesting. But that again is maybe not that important. I'm just gonna mention. Maybe it would be okay to say this is part of longest chain. But what we really need is the Merkle root. This is something that will be interesting, and the timestamp. So once we have a Merkle root, I think maybe we have all the pieces that we can run through the validation. So we're gonna go and import Merkle tree, validate proof, and we're gonna give proof branches. The target hash is transaction ID that we just, and the root which was fine in the header info, header, oops, and the Merkle root. Let me check how this works. True or false? Okay.
I'd make the text a little bigger. Be good.
Yeah, I should have done this sooner. So we're just gonna do something simple for now. Console log validated, like oosh, just with a word. Later I'm gonna put something nicer. validate it. So basically that's it. I don't think there's more to it, but I guess we can stop and say a few words. Plus I could probably make this a little nicer if validated. Let's do that. Oh yeah, I have some idea. File, and we're gonna say, let me rather do with those. I'm gonna say file, dollar, file name, existed, at least, at, and now we say another dollar, and we're gonna say new date, and we're gonna say creation timestamp is the thing. So again, header info, header, and this is in seconds, so we need to multiply by 1000. Else console log validation failed. Okay, one more time. Okay, so I think we put all the pieces together, and I want to maybe stop for a couple of minutes and see what we've done here. So first thing, I'm gonna put this in a first part. We're gonna call it validate content, or content, yeah, validate transaction content, and the second part is validate blockchain existence. Probably bad naming, but so
That's cool. IDE just did that.
sorry.
It's cool your IDE just did that. It just created a method.
Oh yeah, absolutely. I use that a lot. So I wanted to stop and explain what kind of dependencies we have. The proof, if we look at it, where's some proof here? As I said, has just 3 pieces. It's block hash, the Merkle proof, and the whole raw transaction. So once we validate the proof, we need to hash the file, we need to parse the raw transaction and look into it, and we ask the header client service, from which we get a little bit of block header info, and then we have a Merkle tree validation. So there's no dependencies on no services, no party, everything we can do ourselves. If I pack this little algorithm, the proof and the file, and I bring it to anyone, it can be executed anywhere at any time, and we can be mathematically and economically pretty sure, no, very, very sure that this file existed, at least today, right? So that's important for the future if we need the proof. So what's your comment on this? This is pretty cool.
Yeah, this is really cool, and I think some comments on what it can't do, because I think there is a lot of confusion because these SPV proofs come up a lot when you're talking about peer-to-peer transactions, and I think how you stated, this transaction ID contains the message. File Druid existed at least at this time. So like that's pretty much all you can say. So when you're talking about paying Bitcoin outputs, that's not really sufficient proof for a merchant to accept a transaction, because if you're receiving unspent outputs, you can prove that they existed at some point, but what you can't prove is that they haven't been spent already.
Yes, this is, I think, causing a lot of confusion, or even some might think maybe you don't understand something, but the in my view, the if it hasn't been spent, only miners can check. But that's a very it's a more complex problem, right? We're talking about Bitcoin, how it works, and double spend issue, right?
Right.
Here, this is very simple. It's just one file. Did it exist or not? Was it time stamped or not? And that's it. It's very simple. It's very simple to verify. There's just hashing, proof of work. There's no cryptography basically. I mean, this is our cryptographic tools, but it's just hashing in the end of the day. Um,
Right.
I think it's very powerful. Like, and we just demonstrated, like, okay, it took us hour and a half maybe, but we actually built that essential piece, right? And
Right.
we can confirm it works, it's valuable, and now we can start thinking to build, something around it. But the
Yeah, I think
basic piece is here. It's in front of us, and we put it together like short amount of time.
right. And hashing a large file like this is pretty high level, but I think it's more interesting to see like how small can you get of like little things you're proving. So it's like, you know, can you get and efficiently like timestamp every keystroke you make on your computer or something, just so there's always proof. Like when you're talking about like, really secure things where you want to like maybe like a database log or something like that. I think something like this is really cool.
Yeah, you can always like abstract, the same structure and build off-chain something that also maybe uses Merkle trees and then just one hash you put on the on the chain. It really depends on the use case, on the context, or what you want to do, how you want to do, how much data you want to save, and where. But just the concept of being able to put a small hash, and then based on this hash you can prove of
Right.
existence of many things. That's very, very powerful in my opinion.
Yeah. Like imagine, services take database snapshots every half an hour or whatever you set it to. Like I think it'd make sense to just hash that and like put every snapshot some hash on chain.
Yeah, I think it's an open world of ideas. The good thing about BSV network is that this is super cheap, right? You can try like without even thinking about certain optimizations, like you know, just write a timestamp. It costs almost nothing, and then go from there. Um, yeah, I guess we should wrap it up. Um,
Mhm.
it was fun for me. Um,
Yeah. Good job.
yeah, thanks for joining me. Thanks for helping me where I got stuck. Um, and hopefully we'll come with some nice other examples next time.
Cool.
Cool. Have a nice day. Have fun.
All right.
Okay. Bye.